Hi everybody, it's Mrs. Westmoreland, and I am here to introduce topic 1.5 about atomic structure and electron configuration. So at this point, you should have already learned about the definition and the periodic trend of ionization energy. So the thing about ionization energy data is that we can use it to predict and support the model that we have of the electron structure of atoms, which is the model of electrons being in specific shells. So the electrons that require the most energy to remove are going to be closest to the attraction of the nucleus. According to Coulomb's law, the smaller the distance, the greater the force of attraction. And then the electrons that require the least energy are going to be farthest from the nucleus. And so, as we'll see in a moment, when we look at the data, there are clusters of electrons whose ionization energies are fairly close in value. These clusters of electrons are going to be found in the same shell or energy level. However, when we see a large jump in ionization energy, that's where we know that the electron is coming from a closer and more strongly attracted electron shell. So here is some ionization energy data for an atom of argon. So you have a data table which shows you the ionization energy measured in kilojoules per mole for each of the 18 electrons that are part of argon's atomic structure being removed kind of one at a time. And then we also have a graph with the x-axis being which electron is being removed and the y-axis being energy in kilojoules per mole. So you'll notice on the graph the energy is negative, but in the data table the energy is positive. That's just sort of a convention where we sort of set the value of the removed electron once the electron is moved has sort of a defined value of 0. So the difference between the initial point on the graph and 0 is going to be the amount of energy that needs to be added or input in an endothermic way to remove the electron. So there's some questions here that I'm going to attempt to explain, showing you the information on the graph. So first we're interpreting the graph. So the first question asks us to put a box around the electrons that are easiest to remove and circle the electrons that are most difficult to remove. So the easiest to remove are going to be the first 8 electrons, the ones with ionization energy values closest to 0. And the hardest to remove are going to be the last 2 electrons, which have the values farthest away from 0. And so based on our responses, we want to talk about how many groups or levels or shells do we think argon has. And so we kind of have this set of the first 8, then we have the second 8, and then we have the last 2. So that would be 3 groups, which essentially represents our 3 shells in an atom of argon. And we can see that we've got a group with 8 electrons, another group with 8 electrons, and a third group with 2 electrons. And so this would be energy level 1, the one that is closest to the nucleus, would take the most energy to remove. This would be energy level 2, and these last 8 would be energy level 3, the ones that are farthest away from the nucleus being easiest to remove. And so the electron from energy level 3 requires the least amount, and the electron from energy level 1 requires the largest amount. And so essentially we're looking at things that, you have sort of assumed about electron configuration of atoms for quite some time, certainly since middle school, that the first energy level has 2 electrons, the next one has 8, and then a third one has 8. And we can sort of see these very large differences between the 8th electron and the 9th electron removed represent going from the third energy shell into the second energy shell, which is of course much closer and much more strongly attracted to the nucleus. And also there's a big jump, a big difference between the 16th electron and the 17th electron. And again, that's going to represent going from the second energy level down to the first and closest energy level, which is the most difficult to remove. Thanks for listening.